Hi everyone, you're watching EE635 Applied Linear Algebra, the 13th lecture. This is your instructor Devasatham, and this would be the first module. So in the past few lectures, we have been pursuing this single elusive problem of block diagonalization of, of a linear operator between in a finite dimensional vector space, right? So far what we have seen is, although we have not actually obtained the answer to this question, but we have made some headways. We have found out that there is this concept called A invariant subspaces, right? And if it is possible to break up the whole space as a direct sum decomposition of these A invariant subspaces, then that leads to this block diagonalization. But the question is, how do we get this non-trivial non-trivial A invariant subspaces whose direct sum is the whole space, right? In this direction, we have found out that one way of getting these A invariant subspaces is to look at polynomials of these operators and look at the kernels or images of these polynomials in the operator. But the question is, which of these polynomials would actually give us these non-trivial A invariant subspaces, right? So for that problem, what we have seen is that there is this special polynomial called the minimal polynomial of the linear operator, which happens to be the least degree monic polynomial that evaluates to the zero operator. Yeah, that is the minimal polynomial of that linear operator, right? But then what do we do with that linear polynomial, with that minimal polynomial? What we'll see in this lecture, especially in this module, is that we'll look at a very fundamental result which has everything to do with polynomials and apparently nothing to do with operators, linear operators, namely the Aryabhatta-Bezu identity. And we'll see that using that identity, using that ancient result, we'll be able to obtain this A invariant subspaces whose direct sum will give us the whole space, and that way we will have this the sought after block diagonalization of the linear operator. Okay, in order to proceed, I will need to share my screen. Right. Fine. So what we are trying to do is, so first recall that V, okay, let me write down that the fact that this is the 13th lecture. Okay, so V is a finite dimensional vector space over the field of scalars F, and A happens to be a linear operator from V to itself. Yeah, the question is to do block diagonalization. Okay, so say mu S in Fs is the minimal polynomial of linear operator A. By the way, there's this curious fact about this minimal polynomial that we'll see now, which will be crucial for us. So let me state this as a lemma. Notice that if, let us define A nu to be a matrix representation of A, which of course is a matrix of size n cross n, where n is the dimension of the vector space, right? then mu a nu is actually equal to mu. I mean, this polynomial is the same as this polynomial. In other words, it doesn't matter which basis you choose, right? You can see it this way. So think of it like this. Suppose you see, suppose I have a nu, right? And okay, here's the thing. I mean, if say f is a polynomial, right? Then if a nu is 0 as a matrix, if and only if a as an operator is a 0 operator in this space, right? Just think about it. Yeah, because of this if and only statement, this whole ideal, the annihilating ideal of the matrix A nu or the linear operator A, they would be the same. That is why the two minimal polynomials are the same. If you don't feel comfortable with this idea, think of it this way. Think of everything in terms of matrices. Suppose A is a matrix already. Yeah, so A is being viewed as a linear operator from Fn to Fn in tuples. Yeah, how does it act? X is being sent to Ax. This is the standard way of viewing linear operators, right? Right. So in this situation, if I use a new basis, so let B be a new basis, for the vector space Fn, and define T as the matrix V1 up to Vn, then we know that A nu is nothing but T inverse AT, right? The similarity transformation induced by the matrix T. Now in this scenario, suppose I look at a polynomial F A nu. Yeah, how is it going to look like? It's going to look like, say, a0 times identity plus a1 times a nu plus a2 times a nu squared plus dot 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 up to a m a nu to the power m, right? Here I'm going to do this trick. I'm going to write this as a0 t inverse t plus a1 t inverse at plus a2 t inverse a nu t, then t inverse a nu t plus dot 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 plus a m t inverse a nu t inverse a nu t, and so on up to t inverse a nu t. How many times? Of course, m number of times. Yeah, but now notice the fact that this thing that I have written here, this t and this t will cancel out. Here also, in between, all the t's will cancel out. What we will be left with ultimately would be a0 t inverse t plus a1 t inverse, oh sorry, these a nus wouldn't be there, of course, my bad, these nus wouldn't be there, it's just a, yeah, they're just a, because yeah, this will be t inverse a squared t plus, sorry, this is at, this is at plus a2 t inverse a squared t plus dot 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 a m t inverse, notice carefully, a to the m t. You see, all the t and t inverses in between just cancel out each other, which then means that ultimately what we are left with is, I can just pull out t inverse outside, a0 identity a1 a plus dot 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 okay, plus a2 a square plus dot 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 plus a m a to the power m and t outside, which of course is the same as T inverse now if A T. So you see, ultimately the identity that we get is f a nu, where f is a polynomial, is the same as T inverse f a t, where where a nu was T inverse a t. So the similarity transformation that takes a to a nu is the same similarity transformation that takes f a to f a nu. Therefore, this implies f a nu is equal to 0 matrix if and only if T inverse, see, because it's T inverse a t, if and only if a is equal to 0. So therefore the minimal polynomial actually is basis independent. It doesn't depend on the basis. It's a property of the operator. All right, so this is a fact that we're going to make use of, right? But then before we do that, what we are going to do now is as I said, that we're going to look at this ancient result from algebra, which we will see how it finally leads to that direct sum decomposition. Yeah, it's a fascinating result. So I urge you, I request you to pay utmost attention, right? If you have any difficulties in understanding, please ask me by email or by posting your comments on the YouTube video or writing on the Google Classroom stream. Okay, so let's start. So the thing that we're going to discuss now is the so-called AB identity, or the Aryabhatta-Bezu identity. What is this? Okay, so suppose f1, I'm not going to write the arguments. F1, f2 are suppose two polynomials, right? And suppose G is their GCD. What is GCD? GCD is that monic polynomial which satisfies those two properties, that G must divide both f1 and f2. First thing, G is a monic polynomial. It divides both f1 and f2, so it's a common divisor. And then if there is any other common divisor, let's say H, then H must also divide G necessarily. Then G is called the greatest common divisor, or GCD. Okay. Now, you remember how we obtained this GCD? The GCD, I'm sure you must have seen this, used this process before. GCD can be obtained by taking, repeated division with remainder, right? The trick applied to positive integers is something that we learn in junior high school, maybe 5th, 6th standards. Or on the other hand, the polynomial version of it is something that we learn perhaps in the 7th or 8th standard. Yeah, so this is it is this polynomial version that we are interested in. Now what was that? So suppose degree f1 was less than or equal to degree f2. What we do is we look at this f1 and then we divide f2 by f1, and suppose the quotient is q1, so we write q1 f1 here, and then we obtain the remainder r1. Of course, remainder has the property that degree of remainder R1 is strictly less than degree of F1. Right? Now notice that if R1 is 0, that means F1 is a factor of F2. Then of course F1 would be, the monic version of F1 would be the GCD of F1 and F2. Right? Because it would satisfy those two properties. Just think about it. But suppose R1 was not 0, then what we do is we now divide f1 by r1, and suppose q2 happens to be the quotient, so we'll have q2 times r1 and we'll obtain r2 for that remainder, right? If r2 is non-zero, if r2 is 0, then we will see that r1 must be the GCD, but we'll come to that soon. Suppose r2 is also, okay, suppose r2 is 0. Yeah, suppose r2 is 0. Let's see what happens. Then we claim R1 must be the GCD G. Why? Here is the reason. First note is that R2 is 0, right? So that means I can write, so that means F1 is indeed equal to Q2 times R1, right? Which means, which implies R1 divides F1, right? On the other hand, on the other hand, what is R1? R1 also is equal to F2 minus Q1 F1, right? Which means F2 is equal to Q1 F1 plus R1. Now you see R1 of course divides R1, and R1 we have seen divides F1, which means R1 must divide all of this sum, right? If this is a factor of R1, this is a factor of R1, the sum of these two things is also a factor of R1, which then implies R1 divides F2 also, which means R1 indeed is a common divisor. R1 is a common divisor. Now comes the interesting part. But why is the greatest common divisor? So that means if there is any other common divisor, that must also divide R1, right? So let's see, how do we get this? Okay, so first we notice that that R1 is equal to, how did we get R1? We did F2 minus Q1 F1, right? That is how we got R1. Okay, now suppose H is a common divisor. So H divides F2, H also divides F1. So this implies F2 can be written as some say A2 times H, and F1 can also be written as some A1 times H, which would then imply R1 must be equal to F2 minus Q1 F1, which I can write as A2H minus Q1 A1 H, which is the same as A2 minus Q1 A1 into H. You see, R1 also is a factor of, is a multiple of H, which then means H divides R1. Yeah, so the monic version of R1 is going to be the GCD, right? So here we see that this remainder, the one that divides F1, so R2 is 0, is indeed a greatest common divisor. And this may seem a little special, so let us try and carry out this a little longer. So we started with F, what was it, F2 dividing, sorry, F1 dividing F2, degree of F1, yeah. So F1 divides, first we divide F2 with F1, we give Q1 F1, we obtain remainder R1. Then we use remainder R1 to divide F1. So this is Q2 R1, remainder is R2. Let's carry out one more step. And this is, let's say, R1. This is going to be R1. So this, let's say, is Q3 times R2 and R3. And suppose now R3 is equal to 0. The next step, the next case. So if R3 is equal to 0, then once again, just going backwards, just working our way backwards, we'll be able to show first thing that R2 would divide both F1, R2 would divide F2. So this goes to you as a homework. Show that this is true. What more would be true is the following. So first we show, we notice that R2, how do we get R2? R2 is nothing but F1 minus Q2 times R1. That is F1 minus Q2 times, but how do we get R1? R1 is F2 minus Q1 into F1, right? This is what R1 is. Yeah, F2 minus Q1 F1, right? So now taking all the F1s together, we get 1 minus Q1 Q2 times F1 plus Q2 times F2. Right, I made a mistake here. This is 1 plus Q1 Q2. This is a minus Q2 times F2, right? So, so suppose from this, once again, if H divides both F1 and H divides F2, this would imply H would be equal to some, sorry, this would mean F1 would be equal to A1 H2H, and F2 would be equal to A2H. Putting these two things in the equation, in the above equation, we get 1 plus Q1 Q2 times A1H minus Q2 A2H, which then tells us that this is nothing but 1 plus Q1 Q2 A1 minus Q2 A2H, which implies H divides R2 as well. So once again, R2 happens to be a common divisor, the greatest common divisor, the monic version of R2. So the monic version of R2 is the greatest common divisor, G, right? So the crucial fact that lets us claim or infer that this, we keep dividing with remainders, we go to the final remainder beyond which it's a divisor, it divides completely the earlier remainder, then that last remainder would be called the GCD, right? We've been able to show this because of this particular result. You see, in both these cases, we obtain this particular fact that this remainder, which is the GCD, the last remainder, is a factor times F1, then another factor times F2 and their sum. Yeah, consider this as a polynomial, with the minus sign, a polynomial, right? This is Aryabhatta-Bezu identity. So Aryabhatta-Bezu identity would say that so AB identity would say two polynomials F1 and F2, right? And let G be their GCD. This implies there exists a polynomial A1, a polynomial A2, such that G is the linear combination of F1 and F2 like this. This is Aryabhatta-Bezu identity, right? Fantastic, no? So go ahead and convince yourself that this is the case. So this goes to you as a homework. Take various polynomials and verify this fact, right? One crucial outcome of this is the fact that if there are two polynomials which do not have any common factors, so their GCD, the monic GCD would be 1. So in that case, we would be able to write 1 as a linear combination of the two polynomials. In that case, these two polynomials would be called co-prime. So two polynomials F1, F2 are called relatively prime or co-prime if their GCD is 1. In that case, there exist polynomials A1, A2, such that a1 f1 plus a2 f2 is equal to 1. Notice that this is true as an identity, which means doesn't matter what value s takes. It's not an equation. Remember that it's not an equation. It's not like this is okay for this, from here I have to find out the value of s. No, it's an identity, which means it's true for all possible values of s. It doesn't really depend on the value of s. S can be any variable. Yeah, this is satisfied as an identity. You replace s by x, you replace s by whatever you feel like. It will still be true as long as that variable admits squaring and taking linear combinations, squaring and taking various powers and taking linear combinations with coefficients coming from the field, right? So in the polynomial ring, this is true. This is the Aryabhatta-Bezu identity. Now the question is, this is all about polynomials. How does it help us in our quest? Remember, our quest was to find out block diagonal representation of a linear operator. And the way to do it was by decomposing the whole space into direct sums of A invariant subspaces, right? Here is the thing, here is the trick. So this is one of the most important theorems or lemmas in this course. Yeah, that's what we're going to see now. Okay, so pay attention. So coming back to coming back to our vector spaces and linear operators. So let me remind you, my A is a linear operator from V to itself, where V is a finite dimensional vector space. Dimension of V is n less than infinity, so it's a finite dimensional vector space over F, over the field F, right? Okay, now let mu s be the minimal polynomial of A. Okay, now let P S Q S be co-prime polynomials such that mu s is equal to the product of PS and QS. Such a thing is not completely outlandish. This is called a co-prime factorization of the polynomial mu s. Such a thing would exist as long as mu s is not what is known as an irreducible polynomial. If it's an irreducible polynomial or an irreducible polynomial raised to a power, yeah, then we'll be able to factorize the polynomial like this into co-prime factors. Yeah, like the way we factorize a positive integer into prime numbers, prime powers. So unless mu itself is a power of a prime or an irreducible polynomial, you will be able to factorize the polynomial into such co-prime factors. So mu is a product of two polynomials such that the polynomials are co-prime. So like for example, mu s could be s cube plus my favorite polynomial is 6 s squared plus 11s plus 6. In that case, I can factorize this as s plus 1, s plus 2, s plus 3. These are co-prime factors. So you can say that, okay, my P is this much and my Q is this much. This could be P, this could be Q. See, they don't share any common factors. So their GCD is indeed 1. So this is what I mean when I say it's a co-prime factorization. Then the lemma says the following. So lemma, we're going to call this lemma a name. What should we call it? Say lemma lemma co-prime. So this is a co-prime lemma. What does co-prime lemma say? So given the factorization of mu like this as done in equation 1, given a co-prime factorization of mu as in equation 1, we have the following. Brace yourselves. vector space V is the direct sum of kernel of PA and kernel of QA, right? Why is this true? So because it's a direct sum, what are the two things that we have to show? First thing we have to show to show that V is equal to kernel PA plus kernel QA is the first thing. And the second thing that we have to show is that kernel PA intersection kernel QA is trivial. These are the two things that we have to show. Okay, so let us see how do we show number one that every vector in V can be written as a linear combination of vectors in kernel PA and vectors in kernel QA, right? Okay, so now remember PQ is co-prime, so GCD of PQ is equal to 1. This implies by Aryabhatta-Bezu identity that there exists polynomials AB such that AS times PS plus BS times QS is equal to 1, right? In terms of matrices, as I said, this is an identity, remember? So I may just replace this by operators also without changing anything. Be equal to the identity operator. Now let V be any arbitrary vector in V. Right? So multiplying V and making this operator act on V, right? Both sides of this identity, the two operators that we have, will make both these operators act on identity. On the left hand side, we'll get A P A V plus B A Q A V must be equal to V. Then we are going to define this vector as W1 and this vector as W2. Define, right? Claim W1 is in kernel of PA and W2 is in kernel of QA. Yeah, want to verify? Notice PA W1 is the same as PA BA QA W1, but remember these are all, they all commute because they are all polynomials in PA. So therefore I might as well write this as BA into PA QA W1, but this is the same as BA mu A W1, but mu A is the zero operator. That means it takes every possible vector in V to 0. So therefore this must be 0. So that means PA W1 is 0, which implies W1 belongs to kernel PA. Homework, show that W2 belongs to kernel of QA. Exactly same way, same thing, right? So that means indeed we can write every vector V as W1 plus W2, where this guy belongs to kernel of PA and this guy belongs to kernel of QA, which then means V indeed is a sum of these two vector spaces, these two subspaces. Yeah, great. No, now we have to show that these two are, their intersection is just trivial. So let V belong to the kernel of PA intersection kernel of QA. Okay, once again we use AB identity that says identity operator is equal to A PA plus BA QA, right? Which then means V multiplying, making these operators act on um, act on V, right? But V belongs to the kernel of PA, so this must be 0. V belongs to kernel of QA, so this must be 0. Both are 0, which means V is 0. So only the 0 vector is there in the intersection. So this implies kernel PA intersection kernel QA is just 0. So this is what we wanted to prove, right? So now we already have, you see, we already have via this lemma coprime, we already have a direct sum decomposition into two invariant subspaces, because this W1, which has been defined as kernel of PA, this is A invariant. We have seen before that any polynomial, you take any polynomial in the operator, look at its kernel, it's going to be A invariant. W2, which is defined as kernel of QA, is also A invariant. So I already have factorized, my whole space into two, into a direct sum of two linearly two A invariant subspaces. So then choose a basis for W1 and choose a basis for W2, right? So then this B defined as union of B1 and B2 will be a basis for the whole space, because their direct sum is the whole space, right? Is a basis for V, and because they're A invariant, under this basis the representation of the operator A is going to be A11, 0, 0, A22. What will be the sizes? This size, let's say, is going to be, okay, let me not use this symbol because it has a different meaning. This is, let's say, K1, K1, this is K2, this is K2. What do we know about K1, K2? K1 must be the dimension of W1 and K2 must be the dimension of W2. What do we know about this? This is dimension of kernel of PA. This is dimension of kernel of QA. So look at those two dimensions, obtain these two bases for these two subspaces, put them together as a union. That gives you block diagonalization. The question is, this is just one step, no? We wanted to write this matrix A into as many small chunks as possible. So smaller and smaller such diagonal blocks is what we want. Yeah, how to do that? We'll see that a repeated application of the coprime lemma will lead to that particular decomposition of the whole space. Yeah, that is what we will see in the next module. Okay.